Okay, so today is our second consecutive lecture about shortest paths. But today we're going to be doing two variations. One will deal with negative edge lengths. Last time we did unweighted and positively weighted. And then we're also going to do all pairs shortest paths, where we want to get all pairs of distances. So, yeah, okay, so we've been doing graphs a little while. A week ago, we did the strongly connected component stuff, reachability, this very slick way to use depth first search to get all the strongly connected components in linear time. Uh, and then last time we did positive edge weights and shortest paths. And it's, we're basically doing, the key point I think was doing induction, in distance or order of distance from S, one way or another. And it was only kind of like after establishing the 10 closest were correct, could we feel good about the 11th and 12th? And ultimately, that's what the correctness relied on. And I think it's not captured in this slide here, but a big theme also to keep in mind that you'll get a lot of practice in the upcoming homework is, I might give you a simple problem and you're like, I can just hack and open up Dijkstra and it'll be very tempting, but consider changing the graph instead of changing the algorithm. You won't have to reprove so much. You would need to do a quick if and only if, but it's much better than like going through all the motions that we did for Dijkstra's algorithm or something. And you'll find that you'll be able to solve much more complex problems this way, right? It's really about kind of understanding conceptually, what a graph is, what the algorithm does. Yeah, but you'll see. Okay, so today we're doing negative edge weights. So same basic setup as before. I want to get from S to T, but now I have some negative edge weights. Okay, so you're just looking for walks to get from S to T. Sometimes the distance will go down and stuff, right? So just to make sure we're on the same page, thought we could all stare at this one and try to figure out the distance from S to T. Anyone find one? What's the best? Anyone want to suggest one? 0? Okay, how do I go to 0? So I start here, right? Right, right. So 3 minus 2 minus 1, 0. Anyone beat 0? Yeah. Okay, okay. Like that. Like that. Oh, addition. Okay. 1, -9, -12, -11, -9, -10. Yes, -10. Anyone do better? Yeah. Yes, there is a loop -1, 2, and 5, or -1, 5, and 2 in order. Sorry? Yeah. Okay, so you're talking about this one here, right? Yeah, so that's like a net of like -93. So there's a negative cycle in there. So I should go through it like as many times as I can. Okay, so if I'm starting at S, how do I do that? So this was the same graph with numbers now from before. That was that triangle that you actually can't reach in the middle. So there is a negative cycle, but actually doesn't affect us here. But it is something that we will have to be worried about today. Okay, but at least we're all on the same page. I think, it's also interesting to point out, like, I do think -10 is the best, at least for many years now, that's the best we've gotten. But it's still like you stare at it and you're like, not really sure. if it's the best. You're like, I think I've exhausted everything, but it's not clear like how to prove it or kind of, yeah, easily check a solution. So, all right, so negative edge length is going to present, well, several issues, but maybe I've reduced it to two. So there's Dijkstra's algorithm in the top left, the unoptimized version, just, greedily trying to find the next closest vertex, next closest vertex, next closest vertex. And here's like a very simple graph, right? And if I'm starting from A, what would Dijkstra do? The closest vertex will be B. It'll say, oh, that's distance 1. And then it'll say, oh, what's the next closest one? That's D, that's distance 2. And it'll conclude that D is at distance 2 before it realizes that, C is 3, and then you can go this way to get 1. Right? So that's just a simple example that Dijkstra will get wrong because it's going to sort of assume that you're done before you've actually exhausted everything. Okay. So maybe one way, one thing that sort of breaks your intuition is that the shortest paths don't necessarily go through the closest vertices. Okay, that's sort of weird. So that sort of natural inductive hypothesis or natural kind of greedy approach, at least that observation is not come for free this time. Okay? And here's a second thing that we just kind of worked with, right? This came up in the example a moment ago. If you're going from S to T here, right, you could just go straight across for distance 3 or something. But you can go and you can do one loop. Now you're down to 2. You can do 2 loops. You're down to 1. So each time you do a loop, it goes down by -1, right? And you can do this as many times as you want. So there's no lower bound. You can make it arbitrarily negative. So we call that just negative infinity when there's no lower bound. Okay, so that's the other maybe wrench that we're throwing into the problem when we introduce these negative edge weights. So we're taking on one hand sort of a simple or natural question like how do I get from point A to point B the fastest? But we have these negative edge weights which are kind of break some of our intuition, and we might find ourselves asking questions like this. How do you deal with negative cycles? Maybe identify them and stuff like this. Yeah, one interesting point is, when all the edge weights are positive, there's no point in having a cycle because that would only give you a positive distance, right? But that's not necessarily the case anymore. So, strictly speaking, the distance was defined as the infimum length over all walks, allowing for things with cycles and stuff, right? So we want to tease apart like, well, what is the difference between shortest path and shortest walks here and just clear up that sort of confusion. And then lastly among what I had is when we start trying to prove these things or trying to come up with an algorithm, and we want to eventually prove it, we also need some kind of inductive hypothesis. And at least the attitude or approach we were taking last class, that doesn't work, right? This kind of natural idea of closest vertex, second closest, third closest, we already saw, that simple example where that doesn't go as cleanly, right? So we want to make some kind of principled sound algorithm, but here, it's not clear how to kind of build up a solution incrementally, right? How to take sound steps in a way. Okay, so that laid out. Okay, so I want to first just clear up then this point here about shortest path versus shortest walks. Okay, was the following just lemma to get us started. All right, so let me read it slowly. So suppose I have 2 points S and T, right? So I want to clear up 2 things, like what's going on with these negative infinite distance, and then do you have a shortest path or shortest walk or whatever. So this lemma says the distance from S to T is finite if and only if it's attained, by a path. Okay, so if it's not a negative infinite distance, okay, there is a finite thing, it's 5 or 10 or -10, but the point is it's finite, it's not negative infinity, then there's going to be, in fact, be a path from S to T of length -10. Does that make sense? So at some level, because we often talk about this problem as like shortest path, and that's like a little bit confusing because with negative infinity, you might not want to use paths, so to speak. But this is really saying every time the distance is finite, it is realized by a path. Okay, and it's an if and only if. Okay, so that really clarifies at some level that these negative infinities are really caused by cycles. But okay, let's just prove this one structural thing, and then I think that will sort of at least clarify this negative infinity issue, and then we can really focus on the algorithmic part. Okay, so we start with a little bit of structure. Any ideas of how to prove this? Is a statement okay? Let's just go through both directions. So I think the first direction, I'll just do if. So okay, suppose a distance is attained by a path. Okay, so suppose you have some s to t, and there's some, oh, I guess that w should be a p, sorry. Okay, suppose there's a path that actually attains the distance, whatever the true distance is, then of course, a path is finite, so that gives the distance. Okay, so that direction of the proof is not so interesting. The more interesting part is only if. Okay, so suppose I told you all you knew about S and T is that their distance was finite. Okay, the claim is that you're going to be able to get from S to T along a path with that distance, and that the extra flexibility of a walk and allowing for cycles isn't going to really help you. Okay, that's the claim. Yeah. Oh, I should probably clarify. Yeah, so here I'm going to mean a path to mean I only visit each vertex once, which also implies you can only use each edge once. And a walk is allowed to revisit vertices. I probably should have said that first. I do this all day, so I take some of these terms for granted. So in particular, I'm talking about paths where you don't repeat vertices and walks where you're allowed to repeat vertices. Okay, and try to tease apart this issue of cycles and non-cycles and stuff like this. Okay, so suppose I told you that the distance from S to T is finite. The claim is that I can get from S to T without using any cycles at some level. Thanks for asking. Yeah.
I'm just confused about the earlier question, right? Sorry, if we're guaranteeing that the shortest distance from the shortest way to get from S to T isn't infinity, then doesn't that by definition mean that it's going to be a path where each vertex is a visit once? Because if you would have a reason to revisit vertex, then it would end up being that price.
So let's just tease that out. I think that's basically what we're teasing out. So let's just try to get that written out. Yeah.
I think kind of going off of that, maybe you could split it into two cases. So like a positive cycle where you have no reason to take it, and a negative cycle where you get a negative infinity pathway. So you say, oh, we know that the distance is finite, and we know that there's no reason to take a positive cycle, so we know that there's no cycles. Something like that.
Perfect. So I think we're all on the same page here. All right. So imagine you have some walk, and if there is a cycle, okay, the intuition's like, well, positive cycle, you should just get rid of it, right? If you're going in a loop and you're just adding distance, why would you do that? And then you all have your eye on these negative cycles. If a negative cycle, then you should be able to get to negative infinity or something like this. Okay, so I think that's exactly the idea, and it seems like I'm getting a lot of nods. So that's the intuition. Let me just go slowly through kind of writing it out and setting up this proof by contradiction. So here's maybe one trick that's helpful, just a subtle trick when you write these things out. Okay, so in your minds, you all had imagined some kind of walk from S to T, and you're like, well, why would there be a cycle? And I think that's what a lot of people were kind of going through. Okay, so here's what I'm going to do. I'm just going to add the word, the second part, minimum number of edges. Okay, so out of all the ways to get from S to T with minimum length, so it attains that distance L, choose the one with the minimum number of edges. Okay, and this will, I think, let us say exactly what we all mean, but a little bit sharper, so that we don't have to kind of end this proof with like, there's no reason to have negative, or if that makes sense. So then I think we have exactly those. Yeah. So, all right. So if W is already a path, then you're happy, right? There's a path that attains S to T. So let's say that W has a cycle. That's all what you all had in mind. So the minimum number of edges among all the short ones. And we'll break it up into two cases. I'll just, spew it out. So in one case, you have a positive cycle or non-negative cycle. Okay, this also capture the zero length cycles. If you remove the cycle, you're not going to increase the length, right? Because it's a non-negative length that you're removing. If you're cracking something non-negative, it's only going to go down. But you decrease the number of edges. And this was supposed to be the minimum number of edges, as a tiebreaker. So that's one contradiction. And then let's say that the cycle was negative. Then just going around the cycle one more time should decrease the length of your walk, but the walk was supposed to be already the minimum possible length. Okay, so I think this is what everyone had in mind. And maybe the only slight thing I've added is to focus on the walk with the minimum number of edges as like a tiebreaker. So it's kind of easy to articulate this contradiction. Positive or non-negative cycle, you can just drop the cycle and the distance won't go up, and the number of edges goes down, right? That's where it's nice to have the minimum number of edges as a hook. And then if it's a negative cycle, you should be able to repeat. That I think we all captured. Okay? But either way, you'll get some kind of contradiction to this setup. That's okay, right? I think. Okay, so much for that. Now, that sort of squares that away. All right, so now let's look into the maybe more algorithmic question, which is sort of related to a question of inductive hypothesis. But now we've sort of at least settled this issue of negative infinity versus finite, shortest path versus shortest walks. Okay. That's going to make it easier to reason about some things later on. Now let's actually get to the fun part and try to come up with an algorithm. Right? We want to systematically figure out how to get from S to T as fast as possible. We know that at least something like Dijkstra's algorithm won't immediately work. So any ideas? You might as well guess and stuff before I show the answer. Yeah.
Yeah, I think we learned about some algorithm last semester or in 251,
Oh, fair enough.
where you essentially like added or you assigned like a distance from starting vertex and a previous node to each vertex, and then when traversing, if you reach a node, then you calculate that distance, and then after a certain point, that distance goes down. Now you reach the negative life cycle, and then you can't take it.
Okay, let me try to recap. Okay, so this is apparently something you've already learned in a previous class, but you said you have some distance between two nodes.
It's like you track the distance from S to vertex V,
Okay.
and you store that. And if at some point later after that distance is assigned, that vertex V gets a distance that is less than what it was, or it decreases, then you have a negative weight cycle, edge cycle.
Okay, so there's something about first tracking some kind of distance, and if it goes down in some situation when it shouldn't, then there should be a negative cycle. But we should try to open up what it means to track the distance. I feel like there's a lot that's doing a lot of work for us. Like, what's the first step of the algorithm? What does the computer do first? Yeah. Sorry? Okay, so we can assign all the distances to infinity. Okay. I actually don't quite know what algorithm you guys have in mind. So what do you do next? Okay, so you start with infinity. That's like the best bound you have to start. Maybe S to S can be 0, but. Well, it's fun to guess. Yeah.
If I remember correctly, the algorithm that we learned, there was this state matrix that compared, or that really that had the list of all the edges inside that matrix, and then we kept on applying that matrix onto the original source node, and then if there was ever there was ever like, so something similar to that, if there was ever a decreasing node multiple times, then that would be considered a negative cycle.
Okay, so you had a matrix over edges and you applied it to
So it would be
a state matrix you applied to a source. Sorry?
B-dimensional by B-dimensional matrix where each index represents like the source to or the start node to the end node of each edge. And then each
Like an adjacency matrix?
adjacency matrix.
Okay.
Yes, yeah. And then you apply that out to the source node.
Okay, so you have an adjacency matrix and then you just apply it to the source node.
I'm not remembering the specifics.
By the way, as a grader, I just look for the word just and then we'll just, okay, yeah.
And for Belgian for at least you keep processing all the vertices and then you keep a track of how many times you process them. So if you process them more than 3 minus 1 times, you know that that's negative rate cycles, so you stop processing.
Okay, so first maybe Bellman Ford as a name might ring a bell or something. That is indeed what we're going to develop. And then, okay, you're saying something like we should keep track of how many times I process a vertex. And if it's processed more than a certain number of times, that should be bad news. Okay. Okay, so there's some counting involved of some kind. Anyone? Yeah.
The number of vertices we have for each edge, and then we suppose like intended distance of u already calculated, and then we check like relaxing the edges. If the distance at u plus the edge of v is like less than what has already been squared at distance v.
Okay, so somehow you're setting up some kind of tentative distance matrix and you just keep looping over edges trying to improve things? That some kind of okay. How about this? How about as a slightly easier problem, instead of just trying to get all the distance at once, let me do a smaller problem. Like if I told you like what's the best way to get from S to T using at most one edge? That's fairly easy, right? Just check to see if there is an edge from S to T or something like this. Okay, and if you could figure out how to do one edge, then I asked you, okay, how do you get from S to T with at most two edges, as little as possible? Yeah, that seems at least, once you figured out one, then maybe you could figure out two. Once you figured out two, then maybe you can figure out three. Yeah. So if we actually lift the problem, so I'm not going to try to think of it as directly trying to find a distance from S to T. I'm going to add this parameter K, right? Just counting the number of edges, and that's probably kind of similar to what you had in mind when we discussed counting. But I'm going to kind of lift the problem and add this parameter. And for example, once I start counting edges, I don't have to worry about like infinite loops and negative cycles and things like this, right? Because you can't go on forever if you can only take 10 edges, right? So I'm just going to add this parameter and just kind of like flatten out some of the, or lift out, it kind of lifts above all the, whatever knots are in our head thinking about these negative cycles and weird things like this. Okay, so I'm just going to add this parameter and first just focus on this problem from going from S to T with at most K edges with minimum total length, right? That may be positive infinity to start. And you might find that we come close to whatever you had been exposed to in 251, but I'm going to have maybe a different perspective. Okay, so good. So if we wanted to make an algorithm like this, what would be the first step? Yeah.
Do the basic case,
Okay, what would be the step before that?
the final recursive spec.
Okay, good. We'll define a recursive spec. Great. So maybe I'll do SW for shortest walk, right? And we'll just define our subproblems, right? And we're going to try to define our subproblems so they can kind of solve themselves. We're going to make a recursive algorithm. So anyone want to fill in some parameters and describe what we're trying to solve in each subproblem? Yeah.
The parameters could be like S, T, and K.
Okay, S, T, and K.
Algorithm
as a WSDK, but with the interfaces for SST,
Yeah, maybe min length st walk with at most k edges or something like this, right? Forgive my handwriting. I'm going to use the length of st walk as a distance just to keep it kind of clean and separate, right? But that would be, well, that certainly restates the problem we're trying to solve. But you can also see why this would be very useful as a subroutine, right? You have right now flexibility over both endpoints, and you can go from k down to k minus 1 and things like this. Yeah. So this now you're kind of set up. I think what I had is very similar, but the only difference here, well, I used I instead of k, but that's not a big deal, is I decided just to fix s and vary the endpoint, the destination v. Okay, so I'm trying to get from point A to point B with a certain number of edges. I'm just going to change b and keep a fixed. But both would kind of have been okay. Just this is how the slides are set up. Okay. All right. So now you have this sentence, and maybe now you can see the entire algorithm already at this point. But let's maybe I should erase that. Okay. All right. So let's implement it. Right. So maybe the natural base case is 0 edges. Right. That seems the easiest one. And I set this up a little bit for us. I've made a distinction between when v is the source and when v is not, right? Okay, so for 0 edges, what should these values be? Yeah,
If v is equal to s, then you don't need like you're already there, so 0.
perfect.
And if it's non-s connected anywhere with 0 edges, it's
Yeah, plus infinity. So maybe this reflects this suggestion of kind of initializing some kind of matrix with infinity or something, sort of implicitly similar. Okay. So in the interesting case, you're using more than 0 edges. You 1, 2, 3, 4, 5. Okay, some number I. So how can we, recursively solve this?
we can either like go to v with I minus 1 edges, or can also like substitution of vertex of v with like I minus 1 edges, or at the region like the edge.
Okay, so you're trying to go from S to V. Yeah,
So it's start at v, but you can reverse by like doing the recursive step of each of the like the vertices pointing to v.
good. I think, yes.
I guess v they will not. Then you would reduce I by.
Yeah, so I think you're both on the same page. So you're trying to get from S to V and at most I edges. You can either use that most I minus 1 and just take whatever you previously had, so to speak. Or, if you're trying to get there in 10 edges, then you must get to some previous vertex at 9 edges, right? You don't really know which one is best, but we can just try all of them, right? Okay, so I think this is what you all said. I can go through the notation. So here I'm saying, look, let me go to V and I minus 1 steps. That's one option. The other option is, let me look at all the vertices that go into V. Okay, all these vertices U that have some edge going into V. And I can try to get to U with 9 edges as best possible, and then take that 10th edge from U to V if I was 10. Okay, pretty intuitive. Implicitly in here, there's a loop, but I find it easier to kind of see what's going on in this notation. So these are your options. You can only choose one. How do I kind of figure out which one I want? Yeah. The smaller of the two, so min. Yeah, so now you have an entire algorithm, and it's kind of very clear what the algorithm does, right? Okay, it's a recursive algorithm, so naively, it's not necessarily super fast. But how can we make, yeah,
So just to confirm or clarify, the reason why we have SW of V and I minus one is that because the base is different from the V less than I squared.
why do we have this?
Yeah, the portion of that. Because okay, yeah, it's just because the base. So if we include it in the base case of the green portion, if V equals S and I is greater than or equal to 0, then would we not need that? Okay.
I'll turn it back to the class. So why did we include this line? Or what would have happened if I had omitted this first line? So this one makes sense. I want to kind of use one more edge, right? The second line. But what does that first line kind of, why did we have to have it? Maybe we didn't have to have it. So why did, yeah, anyway, who wants to explain?
Maybe there's some way to like move around like the larger number. Like say we can use like 100 edges or something, but like there's a smaller way. Let's just use like 2 edges that like go to V.
Okay, but maybe something more compact. Yeah.
Because your recursive spec says at most I.
So if we look at the problem we're trying to solve, it's just use at most k edges. Okay. And if we hadn't had that, you would just end up with exactly k edges. And you could look back through your table to check everything. Or you could just, yeah. So the problem we're solving is using at most 10 edges. That means you're allowed to use 9. You're allowed to use 8. So that's what that first line will capture. All right. So again, so recursively, an immediate recursive implementation may not be super fast because you're exploring all these paths in the graph. It'll be super slow. How can you make it fast? Yeah. Yeah, we just save our answers. So if I, just save my answers so I never solve the same problem twice, then I just kind of count up the total amount of work I'm doing across all these problems, excluding the recursive subcalls. Okay, so I'm just going to assume I fill out some table as I go along. It's not so interesting what the table looks like. Okay. So now what does my running time come out to? So at some level, most of these dynamic programming things, the initial setup is just summing up over all the problems, the amount of time I spend on each problem. And you can exclude the recursive subcalls because that's getting captured in the table and things like this. Okay, and it's not a very complicated piece of code. It's 3 lines or something, right? It's like, so for a particular problem, if I'm looking at a vertex V and a particular edge count I, kind of how much time do I spend on that subproblem? And then we just have to add it up.
Oh, the number of edges.
Number of edges. So for a particular vertex V, really the bottleneck is just looping over everyone that goes into V, right? This sort of implicit loop in my min. So I think that's what I had. Okay, so K, just because we're doing up to K edges, at least in this, we're just going up to some K. Eventually we'll set K to be N or something like this. But I wrote 1 in case I had no in degree, plus, whatever's the in degree of the vertex. Okay? And if I sum up the in degree over all the vertices, what do I get? I sum up the in degrees over all my vertices. Yeah. Total number of edges. Okay, so you get like K, M plus N or something. Yeah. I mean, for every subsequent edge, we basically do a pass over the entire graph. Is that okay? But I think the real key thing is to just lift it, parameterize by edges, and then suddenly it becomes much easier to get the algorithm. Okay? The kind of greedy thing from Dijkstra or whatever you want to characterize it doesn't work. It's too tricky. Any questions? Okay, now we're not done yet. So, okay, I didn't erase that correctly. Now, All right, so suppose there's no negative infinite distance, there's no negative cycles in the graph. How would I kind of use this algorithm we developed to get all the distances from some fixed S? Particular, what should I set K to be? Yeah. N? Can anyone do slightly better than N?
N minus 1.
N minus 1. So we know from that thing we did at the beginning, that sort of boring lemma, that everything will be a path if it's finite. And so you only need N minus 1 edges. There's N vertices, but there's N minus 1 edges. So if you loop this N minus 1 times, you'll be done. Not that we really care about the difference between N minus 1 and N, but just to make sure we're on the same page. So, okay. So I can call, I can just run this dynamic programming through N minus 1 steps, and then all the distances will be there. Okay, so at least if everything was finite, we're done. So all that's left is try to figure out how to handle negative cycles. And here I'll call back to some idea of like things keep going down and stuff like this. I think we vaguely had some idea, but we're going to really sharpen this up. Okay, so, all right. So, all right, so yeah, so we had the suggestion about like, oh, certain distances are going down and maybe they shouldn't be or something like this. So let's tease that apart. And I'll start with just a definition. So what we'll do is let's just keep track of the vertices that improve each iteration, right? So I'm looking at distances from S, tracking distances, what I think was a word, right? And as I go from iteration 99 to 100, which vertices had their distance values go down? Okay, and some may stay fixed because somehow the 100th edge didn't help, but some may go down. So A sub k is tracking which vertices had their distance improve in the kth iteration. Okay. All right, so, okay. So, all right, so what does the lemma say about, in particular, A sub n? That lemma from the beginning of the lecture. So A sub n is all the vertices whose distance went down in the nth iteration. Distance from S. Yeah?
If you use N edges, then that means you just repeat a vertex.
Yeah, so if you use n edges, and you're visiting n plus 1 vertices, some vertex must repeat, right? Now, okay, so yeah, let's say you have some vertex in this set A sub n. It's saying, look, somehow when you use that nth edge, you did better than you could have done with n minus 1. Right? So in particular, there's some n edge walk that's better than any n minus 1 or less. In particular, better than any path. So what does that kind of tell you? Yeah.
Must be a negative cycle.
It must be a negative cycle. Or, you know, if it's finite, it shouldn't be improving anymore, right? So certainly all of these in set A sub n, those definitely have negative infinity, right? Okay, so those right away. As soon as one goes down, negative infinity, it shouldn't have gone down if it was finite. So that's okay. I mean, that's all just kind of reading off the recursive spec. What do these values tell you, right? N minus 1 edges, n edges. Oh, okay, something happened. Okay, but that's not necessarily capturing everyone that has negative infinite distance, right? Because you might have to like go around a big cycle before you realize you can improve or something like this. So it is true that we have like some, but not necessarily all the vertices with negative infinite distance. But I want to come up with like a very clean characterization. You know, I want to capture all the negative infinite distances. Maybe before, does that make sense? Okay, so yeah.
Do you use like DFS to see if the true target is being able to reach by one of these nodes, and then if the source can reach one of these nodes?
Okay, so I know that anybody in A sub n has negative infinite distance, and anybody from that can be reached from there will also have negative infinite distance, right? So I have some vertex in A sub n. I know I can get there with very negative value, and then I can walk to someplace else and get very negative value. Okay, so certainly if I ran DFS from A sub n, that will get more that are negative infinity. But how do we know we get all of them? Does that make sense? So it's sound, but we want to argue it's complete. It really, that's a very intuitive idea, right? Okay, here's some that are negative infinity. Certainly anyone it can reach must be negative infinity. But how do I know I get everyone? Yeah,
Oh, like the largest negative weight cycle you could have.
okay.
Like all your edges again.
Okay, so yeah, we said some precise statement about A sub n, but why stop there is what you're saying, right? Why not go up to A sub m or something is maybe one idea. So yeah, at some level, or let me put it this way. Okay, maybe the question is, what is, how should I put this? Okay. How big of a K do I need to run, our dynamic program to have enough information to get all the negative infinities? Okay, not very well formulated, but okay. At some level, like, is A sub n enough? Or maybe A sub n minus 1 minus, or is A sub m, where number of edges enough? Or maybe 2n or n squared. Yeah, yeah.
2n times.
Okay, 2n times. Any other suggestions? How many times to iterate? N squared. We're gonna make a vote. Okay, so you have some choices. I guess n minus 1, n, maybe I'll just cross out. You have n minus n, 2n. I guess m is always smaller. M, n squared. Those are anything else for the ballot? This is just the primaries.
n factorial.
N factorial. That must be enough. Okay, and then of course you don't have to vote. Okay, all right, I'll go in increasing order. First of all, who's not voting? Good, 1, 2. All right, who thinks n will be enough? You suggest n factorial. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, who thinks 2n will be enough? Maybe anything between 2n and n, n plus 1 up to 2n. Okay, that's more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12-ish. Okay, 13. Okay. I think something a little awkward, but between 2n and m, up to m. 1, 2, 3. 3. Okay, n squared. Oh, this is popular on the other side of the room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, okay, interesting. And n factorial. Okay. Well done. Okay, so we're going to show that n is enough, which means that you could eventually argue that 2n and n squared and stuff are enough, and with even maybe easier arguments. But at some level, A sub n is actually going to give us all the info we need, and it's kind of cool if you go through it carefully. So, yeah, I don't know if it's that cool. But anyway, all right, so, all right, here's, okay, so we know that, the union of all A sub k's of all k greater than or equal to n, that should be negative infinity, right? So anything with negative infinite distance, eventually it'll go down. Eventually it'll go down, right? So at the very least, k going on to infinity is enough. So some level, what we're trying to do is figure out the union of all these A sub n plus 1, A sub n plus 2. These are all the sets that keep improving. All right. So, okay, so suppose I have, the set of vertices that improved in iteration 100. okay? And I had the set of vertices that improved in iteration 101. I'm claiming that anyone that improved in iteration 101 must have an edge coming from somebody that improved in iteration 100. Why? I'm saying anyone who improved in iteration 101 must have an in neighbor, someone coming to it, that improved in iteration 100. Yeah.
Is there an iteration of hundreds, which would have been
Yeah, okay, so if I improved in iteration 101, but all my neighbors did not improve in iteration 100, then it's all using like 99 or below values. Right? So whatever value was there from all my neighbors was at most 99 edges. So I shouldn't be able to improve on 101. Yeah, I should have improved at 100 or something. Okay, so because if you improve on 101, then you're really using 101 edges. Someone before you must have improved at 100. Okay, so in this sense, like the sets A sub k sort of, they're not subsets of each other, but one set sort of, its out neighborhood contains the next one, contains the next one, contains the next one. There's some kind of chaining going on. So, okay, so for example, okay, so A sub n plus 1, right? Because I want to capture all the A sub n's. I mean, also A sub k's for any k bigger than n, right? A sub n plus 1 is kind of one hop away. It's in the neighborhood of one hop away of A sub n. Everyone that improves in iteration n plus 2 is at most 2 hops away from somebody, or is 2 hops away from somebody that improved in A sub n, right? It's 1 hop away from someone that improved in n plus 1, and that's 1 hop away from someone that improved in n. Right, so it's 2 hops away. And someone that improved in an plus 3 is 3 hops away from something that improved in iteration n. Okay? An plus 4, that's 4 hops away. Just from unrolling this sort of chaining thing. And so that means that if your vertex goes down at any point after iteration n, including iteration n, it must be reachable from the vertices at iteration 10. Okay, because you're kind of always working within this thing. And so that eventually kind of gets that completeness you wanted, right? So now we have kind of both directions, right? So the second point you already keyed in on, the second point was that if I can reach t from someone an, then it's definitely negative infinity, right? Because I can get to here, negative infinity, and then I can go to t. But the more careful chaining argument shows that this will be complete. It will capture everyone. Okay, so if you are negative infinity, then you should be reachable from A sub n. That's the only way to get there. Okay, so now you really know you get everything, and you only ever needed to go up to A sub n. Is that okay? Yeah.
You explain the subset thing again.
Yeah. That picture's up there. So the claim is that if I improve in iteration 101, then one of my neighbors coming into me must have improved in iteration 100. Because if I think about, there's different ways to argue, but for example, when I compute that 101, I'm evaluating just the values of everyone at step 100, right? And if at 100, everyone was the same as 99, then really my 101 step calculation was the same as my 100 calculation. No data changed. And I would have just gotten the same result. But here I'm claiming that I actually improved in 101. So somebody I came from must have improved in 100. Otherwise, I'm looking at the same data. Yeah. So just that one observation, and then we unroll it all the way through, starting from A sub n. That shows you that there must be some kind of connection. Okay. Okay, so put all that together. So it turns out you just need to run our dynamic programming up through step n. And then you could just do some, depth first search from A sub n. That'll take linear time. And then overall, your algorithm comes out to mn time. Yeah, so you do this table, you fill it out, you know, you do the recursive algorithm through n steps. You run depth first search from there. That'll label everything else as negative infinity, and you're done. All right. Any questions? Yeah.
I'm sorry, I'm a bit confused. You have to check if every single point doesn't change. 100. The 100 is one time, or it's just like the last one.
Say that one more time.
Do you have to check if every point can change the one iteration? There's just the last one. Just check it out.
Well, let me see if this answers your question. You can tell me if I'm getting it right or not. So, okay, so if everything was finite, then a sub n you shouldn't see any improvement, right? A sub n you'll get some vertices that improved, and it could be much more than one. It could be all the vertices. It could be half. It could be some subset. And so all these guys I know are definitely negative infinity. And then from there, I'm going to run depth first search to figure out everyone that any of them could reach. And those will also be negative infinities. And in fact, those will be all of the negative infinity. That's the subtle part of the argument. So I just have to go up to a sub n, and I get some clearly messed up vertices. And then from there, I figure out everyone else it can reach, and now give me all the messed up vertices. Yeah. What's the most efficient way to be at a sub n and get everyone I can reach? So you could, of course, go through every vertex and run depth first search. That wouldn't be a big deal because you're paying mn on the dynamic program anyway. But there is a slightly more clever. You could do it in one depth first search. Yeah.
Maybe add a source.
Yeah, we can add a super source. So, I'll just take my graph and I'll make a new vertex. I'll call it S star or something. And I'll add an edge to everybody in, this would be a sub n in our example. I'll add an edge to everybody. And then, running depth first search from S star will immediately explore all of a sub n and then explore everyone a sub n could use. Yeah, so it doesn't really affect the overall running time here, but this trick will help a lot. All right, any questions about that? All right, I'll go through this part quickly. It's not very important. So that algorithm is from the 1950s. It's Bellman, Ford, but actually it's two more people as well. And I'll only note that only a couple of years ago this was actually improved by somebody, and that was very surprising because and we've all been teaching this forever. I guess I haven't taught it forever, but Mike has taught it forever, and I don't think anyone ever suspected this could be improved. But you can actually improve it, and we still don't know what the best bound is. I only put this in the slides last year because this guy was actually a TA for the class last year. So we're among the people who are working on this problem, and there's been some more improvements since then. Yeah. So usually we don't get to work on problems that are like really old. We just like make up new problems that haven't been solved yet. But this would be an example of a very old problem that we actually don't know the full picture of. Okay. All right. So let's move on to all pairs shortest paths. Okay. We're going to still have negative edges, but I'm going to make our life easier and assume there's no negative cycles. Okay. You can, for example, maybe it's an exercise at this point, but you can take the algorithm we just did and sort of find all negative cycles kind of immediately. But I won't go into that in the interest of time. So let's just assume that there's no negative cycles in this graph, but we'll still allow for negative edges and stuff. Okay. And now my goal is to get all pairs of distances. Okay. So from every S to every T, I want to get the shortest distance. The naive thing you can do just based on our discussion just now is run our Bellman-Ford algorithm from every S. That'll get all the pairs of distances, right? That'll be like m times n squared. Edges times vertices squared, because one of them is edges times vertices. Okay, so our question is, can you do better? What's going on here? Okay. All right. Can you do better? Does anyone want to suggest any ideas for a better algorithm? Yeah.
So like you start on one S, like a random S, then you get the you run your algorithm on the rest of the vertices, or like the distance the rest of the vertices, and then you store that. And then once you like do like maybe your source becomes t later, and then if since you stored it, you can compare it s to t distance, and if it's better than
All right, something like run our Bellman-Ford algorithm, get S to everyone else, and then sort of add those edges to the graph. Like,
I guess you just like store the distances.
yeah, store to this. Okay, so now you have S, but now what?
Then like later, if you go from like I guess it's still like
Yeah, yeah. Oh, okay, this is an interesting idea, especially within the changed. Okay, so let's take this graph. The minimum edge weight I think is -10. I removed that -100 from before, so it's -10. So why don't I add 10 to every edge and make everything non-negative, and then like maybe run Dijkstra from every vertex? That'll be m times n time or something, right? That would be pretty good. Okay, so that makes sense. Let's just change the graph, make everything non-negative, which we know how to deal with really fast because of Dijkstra's algorithm. Yeah.
Sorry, I'm not that really work now. Because
Uh-huh.
let's say we have two cases, right? Some goes from A to B to D with 1 and 1, and some goes from A to D, that's just 2. If you add 10 to A to D, it becomes 12. If you add 10 to 1 and 1, it becomes 22.
So there is a little bit of bias here, right? Because the paths with many edges are taking a bigger hit than the path with fewer edges. So that's in general, that's a nice way of thinking. Okay, let's try to figure out how to change the graph, but we have to be a little bit careful. If we just added the same number to all the edges to make things non-negative, it will bias us towards shorter, fewer number of edges in the graph. Okay, so things will change a little bit. All right, suppose I told us that we were going to do a recursive algorithm, which means we'll start with a recursive spec. Does anyone want to suggest a recursive algorithm for this? Oh yeah, sorry.
We do something similar as last time, but like given I, just find all pairs with the most I edges.
Yeah, so let's do something similar to last time. In fact, this was the initial suggestion. If I can just figure out how to get from S to T and I edges for every S and T, I should be able to figure out I+1 maybe and I+2 and stuff like this. So let's try something like that. Hopefully the sentence, okay, length of the shortest walk S to T was at most I edges. And if we're going to implement this recursively, this should go quick because we've kind of seen this algorithm before. What should I put for the base cases? 0 and positive. So if S is equal to T, you don't need any edges. Otherwise, you can't, you need an edge that's positive infinity. And then what should we do in sort of that generic case? So I'm looking at 10 edges. Yeah. Yeah, that's all right. So it's the exact same thing as before. Okay, so I either use 9 edges or, I pick some previous vertex and get there in 9 edges, add one more edge. Okay, so the exact same algorithm as before. The only difference is we've added another parameter because now we're varying the source and not just the sink. Right? We're changing the start and the destination. Good. So what does our running time look like for this problem, for this version? Before it was MN, right? Because we had sort of Yeah. Yeah.
Question. Why isn't this equivalent to just writing previous algorithm on every vertex?
That's a great question. Let's fill this in, and then I think that'll partially answer it. What's the running time of this algorithm? All right, so how many subproblems do we have? Something like n choices of S, n choices of T, n choices of I. But if I fix S and I sum over all the T, then we should be looping through all the edges once. Remember last time we were able to kind of collapse that by summing up the in degrees? So this should come out to mn squared, where the m is sort of summing up the in degrees over the vertices on the T side. Otherwise, you have n choices of S, n choices of I. Okay, which is, to the point suggested before, the same running time we would have gotten from just running Bellman forward from everyone. And it's not really so different of an algorithm either. Right? It's arguably the same thing as running Bellman forward from everyone. So we haven't made massive progress yet. That said, yeah, so can you do better within this framework without changing, keeping the same recursive spec, right? We can actually maybe try to address especially this middle part here and improve that running time, especially when the graph is dense. If m is like n squared, we're looking at n to the fourth right now. Claiming we might be able to get closer to n cubed with this recursive spec. Yeah.
Where in the algorithm are we varying the source? Like, to me, it seems just already tests.
Okay. So, okay. So that's true. The way this is written. So at the end of the day, you're going to want WSTN for all pairs S and T. But it is true that whenever you call for some S, our recursive algorithm will kind of stay within that S. So it's not a very rich interaction of S's across problems, but it's still defined overall. So if I want to get all the distances and I end up filling in all the S's, I'll still pay mn squared time and it'll go over all the S. But it is true that this algorithm is acting exactly like a Bellman forward by itself for each S. There's no interaction across different S's. But the following idea will actually be a little more interesting in this regard. But still, yeah, so I'm asserting that with this same recursive spec and one clever trick, we can actually cut the running time quite a bit. Okay, so just to get some sense of what this algorithm is doing, I have S, I have T, I'm looking at some length 10 path, and right now this algorithm is sort of guessing the second to last vertex and trying all of them, right, for fixed S and T. And that point of the algorithm is actually where we're going to try to improve. Can we do better, something more efficient than the second to last vertex? Yeah.
If we find the shortest path from F to T, then we also know the shortest path from all the nodes within that path to T.
Yes.
That's what we're trying to write down.
Yeah, I also feel like that's sort of like in reverse. We were able to get the distance for SST because we figured out all the distances in between. Yeah.
I think right now we're just decreasing by one at a time. We need to divide by a
Okay. So maybe we can do better than just this one more edge idea, right? What's better than one more edge?
divide some sort of maybe like a power of two.
A power of 2. What does that sort of translate to? So I think what you're saying for the power of 2, that's sort of like half, right? Maybe we can try to guess the middle vertex. Okay, maybe I can try to guess the middle vertex in each iteration, try to double the number of edges I'm using. Or if I know all the paths, all the distances was one edge, I can figure out 2. At this point, there's no distinction. But if I know all the distances using at most 2 edges, could I figure out everything was 4? Right? If I'm trying to get from S to T and 4 edges, I know all the 2s. I can try to guess that middle vertex. Right? And once I have 4, I'm trying to get from S to T and 8, right? But I have all the things up to 4 edges, I can try to guess the middle 4th vertex. Okay? So sometimes this is called a doubling trick. It's always good to, whatever problem you're working on in research or in life or whatever, see if there's a doubling trick. So, okay, so this is almost the exact same algorithm, it's just a little bit more clever. Base cases stay the same. Okay, one thing a little bit different. Okay, so now I'm going to just focus on powers of 2. 1 edge, 2 edges, 4 edges, 8. In this notation, it's hard to represent 0 edges, so the base cases are a little bit different here, because if you set I to be 0, you'll get 1 edge, right? So now the base cases are, because it's really 1 edge, 0 if S equals to T. I'm assuming no self loops. And the length of the edge, if it's just 1 edge, be from S to T. Otherwise positive infinity. So there's some change in base case only because, at least in this notation, there's no way to represent 0 edges. Okay. Now, I'm replacing I with 2 to the I minus 1 with 2 to the I minus 1. So if I'm figuring out 16, I can either use 8 edges to go from S to T, or I can try all midpoints U, take 8 edges to get from S to U, 8 edges to get from U to T. So I keep doubling, 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 doubling. This version actually has more interesting changes in S, so to speak. Okay. How long does this algorithm take? Assuming we cache our answers. Okay, if we apply dynamic programming. Yeah. N log N? Oh, Mn log N? Okay, why? Okay, so log N choices of, there's log N powers of 2 between 1 and N. Okay, so that's the log N. And now where's Mn coming from? Number of well, so naively, there's N choices of S and N choices of T. Right? So actually there's N squared subproblems from what I can, or N squared log N subproblems. N choices of S, N choices of T, and then log N, of these edge counts, because we're doubling. And how long does one subproblem take? Just one of these. Sorry? Is it N? Where does N come from? Mm-hmm. Yeah, so in here, just looping over U, we're trying all the intermediate vertices. One thing to point out, so M is disappearing because we're not just exploring edges anymore. You're exploring all the intermediate vertices. As you just pay an N. There's none of this kind of collapsing. So you have N squared log N subproblems times N per subproblem. And you're going to get N cubed log N. Okay, but it's just using this doubling trick. Now we're doubling the edge count, and that's much faster. Yeah. Sorry? Well, Mn log N could be better if M is as close as is like N. Yeah, so we don't have Mn log N because we're not just exploring the edges anymore. We're actually trying everyone because you're sort of implicitly building a dense graph with the distances from the previous iteration. Okay, making okay time. All right. So actually, we're going to be able to do just a little bit better. I could give you a quick chance to try to quickly shout out some ideas. It'll also be a dynamic programming algorithm, but it's pretty clever. For all I know, you've already implemented in 251 or something. Okay, something Floyd Warshall rings a bell, maybe? Okay, so here's a different recursion, and I think it's sort of like very creative in some ways. I mean, it's not as natural to me. So let's just first number the vertices arbitrarily, 1 through n. It doesn't really matter what the order is. Okay, so I've arbitrarily indexed the vertices. And now what I'm going to do is I'm going to focus on the vertices. We're going to do something like before in some ways, where I am going to, for various choices of start and end, try to get the shortest, distance. But instead of counting how many edges I use, I'm going to keep track of which vertices I use in the middle. Okay, so I have 3 indices for vertices: start vertex, end vertex, and which intermediate vertices I'm allowed to use. Okay, so this shortest walk ijk is the length of the shortest walk from vi to vj, where the vertices in the middle are strictly from this prefix v1 through vk. So you can only use the first 5 vertices. You can only use the first 6 vertices. You can only use the first 7. All right, so that's the big difference. Let's implement this. Any ideas? Maybe base case, whatever. What would be a base case? Yeah.
Is it kind of similar to the last one? If you can't use any intermediate vertices, it's just 0, like Jay was saying.
Yeah, so in particular, I think we'll do k is equal to 0 for a base case. Okay, because that really means you're not using any intermediate vertices. As opposed to k equals 1, then you can use 1. Okay. And now, in the interesting case, you are allowed to use some intermediate vertices. So you've already figured out like the best distances using vertices 1 through 9, and now you're allowed to use 1 through 10. You're trying to go from one vertex to another. What would you do? So you already know how to use the first 9 vertices. You're trying to see if you can improve by using a 10th. Yeah.
Start to the 10th, like you call it with the shortest path to the 9 to the 10th one. And then like 10th to end, call it the start to the shortest to the end. And you get it on this one.
Right, I think I understand. So if you are going to use the 10th vertex, somewhere between point A and point B, right? So I'm right in the middle at the 10th vertex. The part from point A to number 10 is only using vertices from the first 9. And the part from me, vertex 10, down to B, is only using the vertices from the first 9. Because the 10th one's only going to appear once, right? So hopefully it's written. Maybe not. So, all right, so what was described here was the distance from VI to VK, K is 10 in my example, plus the distance from VK to, sorry, I didn't do that right. So from I to K, using the first K minus 1 vertices in between, plus going from K, vertex K to vertex J, using the first K minus vertices in between. Right, so that represents using the kth vertex in the middle and then small, earlier vertices on either side. Okay, we're not quite done yet. Just some small details to make this complete. So that captures if you,
We just use the K-minus 1 vertices.
yeah, or you don't use it. Right, you don't use it, and of course, you don't know which one is better. So how do I? Yeah. Sorry. Then we take the min. Okay. So we just take the min. So we just, yeah, it's very clever algorithm. Okay, so that would be the algorithm. What is the running time if I save my answers? How many subproblems? How much time do I spend on each subproblem?
And cubes of problem and then multiply all the problem.
So n cube subproblems, I, j, k, each have n choices. And then actually the code down here, there's no loop anymore. We just either add two numbers or we take the one, right? So it's actually constant work here. So the running time is going to be n cubed subproblems times constant time per subproblem, and you end up with n cubed, right? So slightly better than n squared or n cubed log n. Okay, that's the Floyd-Warshauer algorithm. Okay, so that is it. We don't have time, so I won't do this. Maybe I'll only mention what the motivation is. If the edge lengths were all positive, right, after all this work we just did, if all the edge lengths were positive, you could just run Dijkstra from everyone and done mn plus n squared log n time, right? So there is an approach where you try to take all the edges in the graph, make them non-negative in a way that does preserve the shortest paths, and then you can run Dijkstra from everyone. Okay, so maybe I'll turn it into a homework problem or something so you can see the steps going through it. And that's actually the idea that all these new latest and greatest algorithms actually build on, this idea of potentials or something. But yeah, so I just want to mention that. Otherwise, thank you. Sorry I went over again.